Chapter 3 has to be one of the most important chapters that we'll talk about because it relates to this idea of making optimal decisions and what kind of analysis should you use to make optimal decisions. This will relate to decisions like what types of prices should we set to maximize our profits, or what sorts of hiring decisions should we make to minimize our costs, things like that. How should we maximize our productivities? Anytime there's a question that involves the words minimize, maximize, you're trying to make an optimal decision. There are probably plenty of companies out there that make decisions kind of, for lack of a better phrase, just sort of on the fly, throwing a dart at a dartboard. Well, let's set this price. Let's decide to hire this many people and just see how it goes. And again, it's really more or less of an educated guess, and you can't really be guaranteed that the outcome of that decision will be optimal from the sense of maximizing profits or minimizing costs, maximizing efficiency, that sort of thing. But we'll look over some of the tools in this chapter that will help us make those decisions. So just some basic definitions to start out. Optimizing takes 3 ingredients. There's something that you want to be maximized or minimized, something that you want optimized. And again, that could be we want to maximize our profit, or a consumer might want to maximize their utility. A business may want to maximize their market share, or again, minimize too. We want to minimize our costs. Actually, you might think they're completely polar opposite ideas, maximizing something versus minimizing something. But actually, the tools are really similar, and the way you go about solving that problem is really similar. So you have different choices that the business can make or the individual can make, and those choices will result in whether your objective function has been maximized or minimized. So if we want to maximize our profit, then that's our goal, sort of, and the way we do that is by setting a particular price or setting a particular amount of output to sell. Consumers say they want to maximize their utility, that's their objective, and the choices they make are the items that they want to consume. It'd be great if we could just completely maximize our utility as consumers, just make ourselves as happy as we could by consuming all the best things in the world, Lamborghinis, mansions, things like that, caviar. I don't really like caviar. Just think of a really good pizza. That's something that I would enjoy. But most of us face constraints. I would argue that all of us face constraints, even if it be our time. But there are things that restrict our ability to maximize or minimize the things that we want, our objective functions. So if I'm a consumer and I want to maximize my utility, then again, I can make these decisions about what items do I want to consume to get myself the most utility. But there's always this constraint of how much money is in my wallet. If I'm a business, again, we want to maximize our profit, and we might decide on prices and quantities that we want to set. But we're limited in a lot of ways: the competitiveness of the market, how big our current business currently is, lots of issues like that. But you'll need, again, these 3 ingredients in making an optimal decision. So a maximization problem clearly decides that the objective function is going to be maximized, and within these constraints, so you're making choices on those choice variables to try to maximize some objective given these constraints. And again, at the opposite end of the spectrum are the minimization problems, where you're trying to minimize some objective function, like your costs, again, subject to certain constraints. And like I mentioned earlier, these might seem like completely opposite types of problems, but actually the tools and analysis that you'll use are really similar, surprisingly. Well, we mentioned the fact of these constraints that businesses or people feel when they're making certain decisions. And while those things are binding on us sometimes, I'm only limited to how much money is in my wallet, I still want to be able to make the best decision that I can, given this constraint. And so these constrained optimization problems, again, for an example, you're trying to maximize the profit given the amount of capital that you currently have. So even though we only have a certain number of buildings right now, then we still want to make as much profit as we can, given that condition of how much our capital is, how much buildings we have. And you might think of those as more short-run decisions, where you're limited to a certain time frame with the number of buildings you have. But more long-run or long-range planning decisions, you might say, well, in the long run, we might have some more flexibility, where we can decide the best number of buildings that we need, or like I said here, the best number of factories that we need. And so we still want to maximize our profit, though. But in the long run, if one of our constraints is less binding than it used to be, then again, you have a little more flexibility, and you might be able to achieve a higher level of profit than you could in the constrained optimization problem. So when we are minimizing or maximizing something, we're trying to get the biggest net benefit, NB here. Clearly, the definition is pretty straightforward. You're just trying to get the biggest total benefit, but you have to subtract out any costs that you incur in engaging in that activity. So we talk about the net benefit instead of sort of the gross benefit, I guess. It's always fun to tease the marketers and the accountants in the room, because most of the time the marketers, really all they're focused on is the net benefit, trying to reach as many customers as they can, trying to increase sales revenue as much as it possibly can, and they may not take a huge account of the costs of some of their advertising programs and things like that. Whereas if you look at the accountants, where they're keeping track of dollars and making sure everything is paid for, they're a lot more focused on the costs, not so much the benefits or how to get the sales in. So of course economists like to tease both sides, but of course we can make a little mathematical equation here. The net benefit is equal to the total benefit minus the total costs. And we want to choose this level of the activity A that maximizes. If you remember back to the 202 class, the Econ 202 class, you might have talked about consumers maximizing their utility, or consumers obtaining utility from the consumption of certain items. And we discussed this notion that utility increases usually when you're consuming something, but it doesn't do so in a nice, smooth, linear, consistent manner. Usually what happens is after you consume a relatively large amount of something, your utility starts to decline, and it may even become negative. So if you can look at the total benefit curve here, that sort of reflects that kind of an example, where as we increase this activity, sure, I increase my total benefit for quite a while, but it starts to slow down. You can see maybe around the 400 units of this activity that the total benefit curve is still increasing, but it starts to slow down. Its slope starts to flatten out a little bit, and then it sort of peaks out. It looks like around 1,000 units of this activity, and then after that it actually starts to decline. And lots of things behave this way. Things we're trying to achieve behave this way, where the benefit increases, but not in a linear fashion, and it tends to minimize or diminish after a while. And whereas the cost side tends to, again, do what's shown here. Usually we have this period where we're in sort of an efficient area where the total costs are increasing, but they're not increasing all that rapidly. So around 100, 200 units of this activity, the total costs are increasing, but the slope there is fairly flat. So the costs are going up, but not that much, not that quickly. After a while, though, increasing levels of this activity makes the total costs increase pretty rapidly. So when you get in the 500, 600 units range, the total cost is becoming pretty steep. It's increasing pretty quickly. Well, again, I don't just care about the total benefits, and I don't just care about the total cost. I care about the net benefit, or the difference between these two. And if I were to maybe make an Excel spreadsheet with the total benefit in one column, total cost in another column, and then set up this third column, which is the net benefit, and I subtract the two, and I wanted to graph that against the level of activity, I'd get a picture like in the panel B at the bottom, where you get this sort of hill-shaped thing. And of course, if I want to maximize my net benefit, then I want to be at the very top of that hill. I want to be at the highest point on that hill. I can see in my picture here that will occur. It's kind of easy to see where the top of the hill is in panel B, but to be able to sort of trace that level of activity up to panel A, I can see that occurs, at that level associated with the B and the B prime there in panel A. And I can see that I get this maximum amount of the net benefits that is there. Again, we're interested in optimization, getting the absolute most net benefit that you can. There are other levels of activity where you still get your net benefit is positive, like here at point C, 200 units of this activity. So I'm still coming out ahead. My total benefit is greater than my total cost. I still come out ahead. But I can see that that's not as good as that point M, which I'm not sure where exactly that is, 350 units. Point M, obviously in panel B, is a higher level of net benefit than that point C double prime. Even though, again, I'm still, if I just asked myself how am I doing, I'd say, well, I'm coming out ahead because my total benefit's bigger than my total cost. But I can see that I'm not at the optimal point. Same thing at this point D. Again, benefit's still higher than costs, so things sound fine. But I can see that panel B, the D double prime, is certainly not as much benefit as point M is. So again, we're trying to figure out where is the most benefit occurring. I always have to remind students, because we just talked about supply and demand in the last chapter, and I always had you try to focus on the place where these two curves cross. And so you might look at this picture, panel A, and say, well, look, there's one line, total benefit, there's another line, total cost, and I can see they're intersecting. They're around, looks like 700 units of this activity. So maybe that's the best place to be, where the curves intersect. Well, that's going to lead you the wrong way, because where they intersect would indicate a place where total benefit equals total cost. And in that case, you have no benefit at all. Your net benefit is 0. Actually, if you look down in panel B, you can see that. The net benefit is actually 0 at that 700 units of the activity. So in that case, the place where they cross is probably not the best place to be. If we have more than 700 units of this activity, I can see that the net benefit is actually negative, and that's indicated above by the fact that the total cost curve is above the total benefit curve, and that's certainly a bad place to be. So I want to be at point M, just a matter of figuring out where that is, how to get there. I can see point G there. They pick out a couple other points for you to look at. I can see point G way out there at 1,000. And again, the optimal level that I want maximizes the net benefit, not the total benefit. So point G is a point that maximizes the total benefit. You're getting the most benefit you possibly can from this activity. But I can see that my net benefit is going to be hugely negative. So again, the marketer might say, well, point G is the best place to be, but the accountant's going to be terrified at that because the costs are extremely high. So we're trying to maximize the net benefit, not the total benefit. And again, the net benefit is going to occur at that A star, that level M, 350 units. And again, well, what does the accountant want? The accountant wants to have the lowest total cost. Well, for the accountant, the place that happens is actually at the origin, where you don't do anything at all. You don't incur any costs if you don't have any of the activity. So that would mean that the accountant wouldn't even have anything to do, so they shouldn't get too excited about that. So we don't want to minimize our total cost. We don't want to maximize our total benefit. We want to maximize our net benefit, again, which occurs at that point M, 350 units. Okay, well, again, we want to come up with a way, an analytical way of determining where exactly that optimal point is. Where do we get the absolute highest level of net benefit? And the way we're going to solve that is by coming up with some terms called marginal benefit and marginal cost. You see the word benefit there. I mean, we use benefit and cost. Those are pretty straightforward. But there's this term marginal that you may not be familiar with. Or if you took the 202 class, you may have to remind yourself of what that means again. So I get a certain amount of total benefit from changing my level of the activity. A useful term, useful concept is, this idea of marginal benefit. Everywhere you see the word marginal, you can replace it with the word additional, and it pretty much will mean exactly what we want it to mean. So I know that there's this activity level that I'm engaged in, either consuming slices of pizza or french fries, or hiring a certain number of workers, or producing a certain amount of output. I know that as I eat more slices of pizza, or I hire more workers, or I produce more output, that there's a change in the total benefit that occurs because of that. I eat one more slice of pizza and I get more happiness. Or I hire one more worker and I get more output from hiring that worker. Or we increase the quantity that we sell and we get more revenue. So what the marginal benefit tells us is, well, I know that I'm starting from a particular status quo. I've already eaten 2 slices of pizza, or we already have 30 employees, or we've already been producing 200 units. And what I want to know is, I want to make a very cautious decision and say, well, what if I just change this activity by 1 unit? What if we hire one more person? What if we decide to produce one more output? What does that do to our total benefit? Does that make it increase, and by how much? Does it make it decrease, and by how much? Because again, when I'm making these optimal decisions, I want to be deliberate and careful about it. So when I divide that change in the total benefit by the change in the activity, it'll tell me, well, what happens to your total benefit as you hire one more person? Or again, what happens to your total output if you hire one more person? So this marginal benefit is going to be really important for us to look at and to compare marginal benefit with the marginal cost. So what do we mean by marginal cost? Well, it's a very similar definition. There's this particular activity that I engage in, and that activity provides me benefits, but it also incurs costs. So if I'm eating slices of pizza, yeah, it makes me happy, but it probably after a while makes me feel full, or maybe feel sick after a while. If I hire workers, the benefit is that they produce for me, but the cost is that we have to pay them a wage, salary. If we produce output, then the benefit is it generates revenue for us if we're able to sell it. But of course there are costs associated with producing the output too. And so again, I want to make this deliberate decision about what is our status quo right now, how much are we producing, how many workers are we hiring. So what will happen to our total cost if we were to increase that activity by just 1 unit? Again, you may have a situation where you don't just do that. Maybe you hire 5 people. And you say, well, we decided to hire 5 people. And you want to say, well, what happens to our total cost after we hired those 5 people? But you want to put it in you want to standardize it and put it in sort of a per unit term. So that's why we end up dividing it by the change in the activity. So when we hired 5 people, then our total wage bill went up by, I don't know, $300,000, let's say. So that would mean that your change in your total cost was the additional $300,000 that your company had to spend on those 5 employees. So the change in the activity was an additional 5 employees. Well, again, the marginal cost will kind of give you a sense of the per unit increase in total cost that came about from that. Again, I'm getting a sense of how my total benefits are changing by looking at the marginal benefit, and I'm getting a sense of how my total costs are changing by looking at the marginal cost. So I sort of hinted at this already. The great thing about these marginal variables is that they tell me about how quickly the total variables are changing. So again, if we hire another person, I know that my total costs are going to go up because we have to pay them. And I can get a sense of how quickly my total costs are going to increase, how fast they're going to increase, because that's the worker's wage, that's the marginal cost. If I hire one more person, how much are my total costs going to go up? Well, they're going to go up by the marginal cost, how much additional wages you have to pay for that person. A nice thing that's going to help us solve this optimization problem is to know that the marginal benefit and the marginal cost are the slopes of the total benefit and the total cost lines. So we'll be able to use that to make these optimal decisions. So let's reproduce those two curves right there. Here's my total benefit and my total cost curve. And if I think about the slopes of things, I mentioned this before, the total benefit line, I can see that it starts relatively steep compared to the total cost at least. So my total benefit line is fairly steep, and as I increase my level of activity, the total benefit increases, but I can see that the slope is starting to slow down. The slope gets flatter and flatter until it tops out at around that 1,000 units of the activity, and then after 1,000 units, the slope of the total benefit line actually becomes negative. So I start with a fairly steep slope at 0, and the slope becomes more and more flat, I guess if that's a way to say it. The total cost line kind of does the opposite. The total cost line starts flat, and it becomes steeper and steeper as time goes on. Well, I can translate that into these notions of marginal benefit and marginal cost. So again, the total benefit line starts fairly steep or with a high slope, and then as the activity increases, the slope slows down, or the slope gets smaller and smaller, until eventually the slope becomes negative after 1,000 units. So I can see that by looking at the marginal benefit line at the bottom. And it starts out fairly high, close to 8 marginal benefit, and it becomes smaller and smaller until it crosses the 0 point at 1,000 and becomes negative after that. Again, total cost line starts out fairly flat, and it becomes steeper and steeper, and that's what the marginal cost line is doing. One thing you might notice by looking at the picture is to say, well, I knew I wanted to be at those points B up in the top. I wanted to pick my level of activity that was associated with that point B. Well, how do we know where that is? You might be able to eyeball it somewhat and get kind of close. One thing that is true at that point B is if you look at the slopes of the two lines, the total benefit and the total cost line. When you're at 0, I can see that the total benefit line is very steep, total cost line is fairly flat, and as I move away from the origin towards that 350 units, I can see that those slopes, I still have a total benefit line that's steeper and a total cost line that's flatter. Until I get to point B. When I get to that point B at 350 units, the slopes of those two lines are equal to each other. If you can't see that, go to the other end. Go to about 700 units, where the two curves cross. Where the total benefit and total cost cross at 700 units, now the total cost line is steeper and the total benefit line is flatter. So the two slopes are unequal there. And if I move backwards towards 350 units from 700, I can again see that the slopes start to become more and more equal. And I can see that in the graph below, too, that when I'm at 0, when I'm near the origin, the marginal benefit line is a lot higher than the marginal cost line. When I'm at 700 units of the activity, the marginal cost line is a lot higher than the marginal benefit line. But again, there's this interesting result that the slopes of the line are exactly equal at the optimization point. And so I can use that to my advantage by looking at the point B in the bottom graph. I can say, well, I know that where the slopes are equal is going to be the place where there's the greatest distance between the total benefit and the total cost line. So my optimal decision will be, again, where that gap between total benefit and total cost is the greatest, the vertical gap. And that happens down below at, now I got a place where those two curves cross. That's going to be an important point for this one. It kind of looks like a supply-demand graph down there anyway, doesn't it? So where they intersect at the point little b down in the bottom graph, that's the point where marginal benefit equals marginal cost. And once I know where that happens, I know that that is the place where the biggest gap between total benefit and total cost occurs. And that's why optimization occurs. Any of these other points you can consider are going to be less net benefit. Again, there may be other times where you're not exactly sure where that happens, but if you're able to observe what the marginal benefit and the marginal cost is, you might end up in a situation where your current marginal benefit is greater than your marginal cost. And you're trying to figure out what to do. Is this the right amount of activity if the marginal benefit is greater than the marginal cost? And again, you might think that, well, that's great because you have more benefit than cost now. If your marginal benefit is greater than your marginal cost, you have more benefit than cost, so yeah, keep doing that. But again, we're talking about not total benefit and total cost. That would be true. I mean, we want the situation where the total benefit is the greatest compared to the total cost. But here, if we're here looking at the marginals here, then this is really not the place to be. If your marginal benefit is greater than your marginal cost, you want to continue doing the activity. You want that level of activity, maybe consider the next one. So the activity level should be increased to reach the highest net benefit. So that was near the low end of the activity level on the previous graph, maybe around 100, 150 units. There, the marginal benefit was greater than marginal cost, and we would say, yeah, you need to continue that activity and keep going. You might go too far, where your marginal cost is greater than your marginal benefit, and this is where you'd want to reduce the level of activity that you're undertaking. So that would be maybe around 500 units in the previous graph. So the optimal level of the activity is going to be where they're exactly equal. And again, maybe put this in different terms. If you think of hiring workers, and you say, well, I know that the workers generate a certain amount of productivity, they generate a certain amount of output that we can sell, let's say. So some revenue that worker generates, but we have to pay them a certain wage. So if the marginal benefit is the additional revenue that worker brings in, and the marginal cost is the wage, then let's say we have a certain number of employees now, and the last employee that we hired generated $150 for us, and we had to pay them $100. So their marginal benefit was greater than their marginal cost. Well, you certainly want to keep that employee, and you may even consider increasing your employment levels a bit. You may at least consider hiring one more person. When you increase your activity, your total benefit is still going to increase, but it's going to slow down a little bit. As you increase your activity, your total costs are going to increase too, and they usually increase a little bit faster. So if the marginal benefit, if the revenue coming in from this worker is greater than the cost, then you certainly want to hire that person. But what if you've done so much hiring that the cost of hiring the worker, $100, is greater than the revenue coming in? So we have to pay this person $100, but the revenue coming in is only $80. Well, now you've got your marginal cost greater than your marginal benefit, and that would be a person that you'd want to let go. You want to decrease your employment levels at that point. So again, this optimal level of activity occurs where both of these two are equal. So how can I use this marginal analysis to figure out the most optimal level? It's pretty easy when you have this hill-shaped thing, because you just say, well, I want to be at the top of the hill. I can see these two different points, point C and point D, where marginal benefit is greater than marginal cost at point C, or the marginal benefit is less than marginal cost at point D. And I can see, at least in the picture, that I'm not at the top of the hill, so I know that's not the best place. If your marginal benefit is greater than your marginal cost, you know you're not at the top. If your marginal benefit is less than your marginal cost, you know you're not at the top. If they're equal, though, then you know you are. Well, it might be kind of difficult to get the exact equality that you want between marginal benefit and marginal cost, because for certain things it's just difficult to pick 0.5 of something or 0.778 of something. So when your choice is hiring numbers of workers, well, we can either hire one person or two or three, then you're sort of stuck sometimes with making a choice where their marginal benefit and marginal costs are not exactly equal, but we can still approximate an optimal decision with that. Other choices, you might have a lot more flexibility. If you're trying to set a price of something, you don't just have to charge $1 or $2 or $3 for something. You can charge $1.25 or $1.26, that sort of thing. Again, anytime the marginal benefit is greater than the marginal cost, you want to increase the activity. Anytime it's less than that, you want to decrease the activity. And so you want to get as close as you can to marginal benefit equaling marginal cost. And if you can't do that, then you try to pick that amount of the activity where the marginal benefit is closest to it but exceeds it a little bit. We talked about marginal cost and how it's very important. And marginal cost was the idea of your total costs change by a particular rate once the level of activity changes. There are other concepts of costs that we don't want to think about. Well, we can talk about them, I guess, but they're not going to be relevant to the optimization decision. So 3 of them: sunk cost, fixed costs, average cost. Sunk costs are those things you've paid in the past, and we tend to have emotional attachments to these things. You might have sunk a lot of time and effort and energy and money into a particular product line that didn't really pan out, and you're thinking about, well, should we just scrap this whole thing and try something new? But there's always kind of some hangers on that said, no, I remember when we tried this advertising campaign and it seemed to work okay, and we put down a bunch of time and effort 3 years ago to get this done, and we should keep doing it just for the sake of that, for the sake of the time and effort we spent 3 years ago. Well, that doesn't really matter, because you can't get that money back. We call those sunk costs. You can't ever recover those. You can't get those back. So they're basically irrelevant to your current decisions. Fixed costs, we'll talk about these later. These are expenses that company has to pay no matter what level of activity they're undertaking. So if I'm running a business, I know that my wages are a cost that I can control, because I can control how many people I hire. There are some things that I can't control, and some costs that I'm going to incur no matter if we produce a lot of stuff or we don't produce anything at all, no matter if we hire a lot of workers or hire none. If you took out a loan to start your business and you have to make these monthly repayments, then it doesn't matter if your business is open or closed, you still have to make those payments. Those are fixed costs that you have to pay. And so, again, those have no bearing on this marginal benefit, marginal cost decisions that you're making. You shouldn't consider fixed costs in these optimal decision making. One cost term that's easy to keep track of are average costs. You just take your total cost and divide it by the number of units of the activity. So I can say we have a certain number of workers, and we just divide that total cost by the total number of workers that we have. That'll give you kind of an average wage or an average salary. But again, well, just like for the other two, the optimization depends on what's the status quo right now, and we're considering making a 1 unit change of the activity, and we want to see, is that a good thing to do? So again, sunk costs don't affect that, because those are costs that we paid a long time ago and we can't get those back. Fixed costs don't matter in that situation either, because, well, I got the status quo, and whether I increase the activity or decrease it, those fixed costs are always the same, so that doesn't really matter. The average costs don't matter either, because, again, it might be, I've heard it described, if you think about your grade in a course, if you're thinking about should you study for the next test or work hard on the next assignment, maybe in this class we have 8 assignments, and so if you have already done 5 of them and gotten a particular grade, and you're trying to decide whether you should study for the next one, well, if you just looked at your average grade, you might say, well, geez, when I tried really hard for this next assignment, my average grade only went up a little bit. Well, that may be true, but if you study and you work hard for the next assignment, the grade on that next assignment might be really high. And so really what you care about is the marginal cost, not the average cost. What happens to our total cost now if we increase that activity by 1 unit? I don't care about how that cost gets spread out over everybody else. These costs don't affect marginal costs. Don't need to worry about them for the optimal decision. You may care about them in other contexts, but if you're considering these optimal decisions, then they're not really relevant. So we have these optimal decisions that we want to make, and every once in a while there are these constraints that we have to put up with. How can we make the best decision given that we have these constraints to worry about? The thing to think about is, how much benefit are you getting for your dollar? How much bang are you getting for your buck? And again, we can think of that in terms of marginal benefit per dollar. And they're both important, because I don't just care about the benefit I get from doing something. If that were true, I'd be buying Lamborghinis all day. I don't just care about the price of things, because if that were true, I'd just be buying ramen noodles all day. But I care about both. The reason I don't buy a Lamborghini is because I get a huge benefit from it, but the price is extremely high. So I don't get a heck of a lot of marginal benefit per dollar that I'm spending. And the reason I don't buy ramen noodles all the time, even though they're really, really cheap, is that I don't get a whole lot of benefit out of it. So again, the marginal benefit per dollar that I spend is not that high either. But what I want to try to get is the biggest benefit per dollar that I can. So this ratio, marginal benefit per dollar, tells me how much additional benefit I get per additional dollar that I spend. We can use this term, this mathematical term, to make these optimization decisions, because I can look at the different things that are providing me benefit, and I can decide, well, should I spend more money on option A or should I spend more money on option B? Option A and option B both give me a certain amount of marginal benefit per dollar, and I can use those ratios to make comparisons and to allocate my choices to give me the most benefit that I can for the money that I'm spending. To make this maximization or minimization decision, given that there's a constraint, what you end up wanting to do is making the choice, choosing A versus B, in such a way that the marginal benefit per dollar is the same everywhere. And again, if I'm thinking about option A or option B, should we produce option A? Should we produce product B? If I'm a consumer, do I want how much apples do I want to buy versus how many bananas do I want to buy versus how many zebras I want to buy? Z. Anyway, well, I get benefit from eating apples and I get benefit from eating bananas. Apples and bananas probably have a different price associated with them. So if the situation is not true, if the marginal benefit of apples per dollar, let's say, is greater than the marginal benefit of bananas per dollar, well, that kind of means that I'm eating too many bananas. I'm buying too many bananas, and I'm not buying enough apples because I'm getting more benefit per dollar on those apples than I'm getting for the bananas. So my choice should be, if these two fractions are not equal, if the marginal benefit per dollar of A is greater than the marginal benefit per dollar of B, well, I need to do more of A and I need to do less of B. So what happens when you do that? Well, when you do more of A, again, you have this kind of diminishing returns. When you do more of A, the marginal benefit of A is going to go down. I started in a situation where the marginal benefit per dollar of A was greater, but as I do more of A, the marginal benefit starts to decline. And I started with the situation where the marginal benefit of B per dollar was too low. And if I say, well, I want to do less of B, well, when I do less of B, then actually the marginal benefit starts to go up. So if I start in the situation where the marginal benefit per dollar of A is greater than the marginal benefit per dollar of B, once I make this optimal choice and say I want to do more of A and less of B, those two ratios become more equal. I make this choice between A and B. I keep doing that until they become equal to one another. And once you've done that, once they're equal to each other, you know that you've made an optimal choice between apples and bananas. You wouldn't feel like buying more apples or buying fewer bananas, or buying fewer apples and more bananas. You'd feel like the choice you made was perfect. Okay, so we have this theoretical idea of optimization down, and you see the nasty word up there. It starts with a C. People get kind of nervous about calculus. Really, all calculus is the mathematical way of optimizing things. And there's lots of weird things like sines and cosines and tangents that kind of muddy things up a little bit. But really, again, all calculus is the method for deciding how to optimize things, how to maximize and minimize things. And so, of course, this is going to be really important for us to know. As I said at the outset, businesses may make decisions that ultimately aren't optimal just by kind of guessing. Well, maybe we should hire this many people, or maybe we should try selling this many units. And, you might be able to get somewhat close, make a decent amount of profit or net benefit, but you're not guaranteed that it's going to be optimal. So if you use calculus, though, you will know that the choice you made, if you follow the rules, is going to be optimal. So calculus is very useful. It's actually not all that complicated. We're going to do it in, 10 minutes of PowerPoint slides, even though there are entire semesters and sequences of classes that do this. We'll do it in a day. We use it to find optimal solutions for things. It's going to tell us exactly where that A star is, that optimal level of the activity that maximizes or minimizes the objective function that we have. What calculus allows us to do is, given the objective function, it tells us how to find the slope of that line. So if I had an equation for the total benefit line, and again, you can think of the total benefit line had this curvature to it, but it had this changing slope. What calculus will allow me to do is to mathematically figure out an equation for the slope of that line. And that's nice because I knew that the optimal level of the activity was where the slope of the total benefit line equaled the slope of the total cost line. So if I have equations for both the total benefit and total cost functions, then once I use calculus to figure out the slopes, I can set those two slopes equal to each other, and that will help me solve for the optimal level of the activity. So here's our two curves again, our friendly TB and TC lines. I see that my total benefit line starts out steep, becomes progressively less steep, regressively steep, I don't know. And I have my total cost line, starts out flat, becomes steeper. I get my hill-shaped net benefit line. Trying to look for this point where the distance between these two is the furthest apart, and I knew that that was the place where the slopes of those two lines were equal to each other. And that would give me the biggest net benefit that I could get. These other 2 points, C and D, were suboptimal points. F was my break-even. Certainly don't want to be there. G was the biggest benefit, but it actually had a negative net benefit, so certainly don't want to be there. Here's my optimal level, 350 units. And again, I can see that the slopes of those total benefit, total cost lines are equal at point A. if I can come up with an equation for marginal benefit, and if I can come up with an equation for marginal cost, I can set those two functions equal to each other and solve for that variable A. And it'll guarantee me the optimal level of the activity. You don't have to guess. You don't have to say, well, it looks like it's about 325, or it looks like it's about 400. No, it'll give it to you exactly. Another thing I can do, if I know this little hill-shaped net benefit line at the bottom, if I have an equation for that, where I plug in a certain level of A and it tells me the slope, then I can look for where that slope of that hill is 0. The hill has a 0 slope at the very top of it. So if I know an equation for the net benefit line, I can look for where that slope is equal to 0, and that'll also give me the optimal level of A. The trick is being able to go from having an equation for total benefit to getting an equation for marginal benefit, and going from an equation for total cost and getting an equation for marginal cost out of it. So this is where we use derivatives, and I know this is a finance term. I don't know anything about finance, so I have absolutely no idea what a derivative is, if you can invest in a derivative, but I don't think you can invest in a calculus derivative, so maybe they have better returns than the derivatives on the stock market. Okay, you're given an equation. Y is some function of X, so the total cost of our company is a function of the wages we're paying our workers, or my happiness level is a function of how many slices of pizza I'm eating. Our productivity, our output, is a function of how many workers we hire. And again, I'm trying to pick an X, a level of X, to maximize or minimize this amount of Y. To do that, we take a derivative, and it has this. It looks like a fraction here, dy divided by dx. It's not really division. You can kind of think of it as just a symbol. Dy over dx tells me something about the equation that's going to follow. I have this equation y, and it's a function of this variable x. So when I do this derivative, it's going to tell me the slope, an equation for the slope of the function y when I plug in different values of x. So I have this different equation that's going to come out of my equation for y, and then when I plug in values for x into this slope equation, or this derivative equation, it's going to tell me the value of the slope of the function y. So there we go. It gives the equation for the slope of the function y with respect to the variable x. If you think about that total benefit curve from before, we said it flattened out right around 1,000 units of the activity. So the total benefit line, if I plugged in a value of 1,000, that'd be some big level of benefit. I don't remember how much it was, but it'd be some huge amount of benefit, because that was the highest point on the total benefit line. But I knew the slope there was 0. So if once I take a derivative of that equation y with respect to the variable x, in this case, once I take the derivative of the equation for total benefit with respect to the variable a, if I were to plug in 1,000 into that first derivative equation, I would get a result, I would get a result back equal to 0, and that would tell me that when x equals 1,000, or when a equals 1,000, then the slope of the total benefit line is 0. Different equations have different numbers of variables in them. If you remember back to chapter 2, we did demand functions that had lots of different variables in there too. And so again, I could look for different ways of optimizing this equation y. I could either figure out the level of x that maximize it, or take a derivative of y with respect to the variable z. Well, there's important ways of taking these derivatives that are going to be useful to remember. Sometimes you have a line that is just a flat horizontal line, and there's really this would be something like a fixed cost, where your cost in this case is equal to 100, and it doesn't matter what level of activity you're doing. You have to pay that $100 lease payment no matter what, no matter if you're hiring a lot of workers or no workers at all, if you're producing a lot of output, no output at all. So in that case, when you change x, when there's a change in x, a dx, there's no change in y. There's no dy. There's no change in the y variable at all. So the slope of that horizontal line is 0. Y equals 100 is a flat horizontal line. So the slope is 0, the derivative there is always going to be 0. Anytime you have a constant, the derivative of that term is always going to be 0. This is one we'll use the most, though. You have a function of y with respect to this variable x, where x has a coefficient out front, b, so b is some number being multiplied by this variable x, and x might be taken to a certain power, to the power of n, x squared, x to the third power, that sort of thing. So again, I want to come up with an equation that will tell me the slope of this line y. When I see this, take this derivative, when I see the dy dx there, again, that's telling me, well, I have this equation y, and I'm figuring out what value of x can I plug in to give me the slope. The way I think about finding the derivative of an equation like this is, well, I have this n, the power term. When I'm taking the derivative, I always think of it as you sort of pull the power down so the n comes out front and multiplies by b. So I've got the derivative of y with respect to x equals, and it starts with this n times b. So these two numbers get multiplied by each other. Then it's multiplied by the x variable again, and I always thought of it as if I'm going to pull one of the n's down off of the exponent, then I got to subtract 1. So I end up with this n times b times the variable x to the n minus 1th power, n minus 1th power, whatever that is. So if I had this equation for y equals 3 times x squared, and you might want to, if you're watching this, you might want to push pause and just open up Excel and make a little picture of what this looks like. Make a column y and make a column of x's, and you can do x's from 0 to 10, and then for your column for y, just say equals 3 times, and then reference the cell number for x, and then take it to the second power. If my memory serves, this will have kind of a U-shape sort of thing. And so the slope changes as x changes. The slope becomes steeper as your x increases. So when I follow this sort of power rule, then I want to figure out the derivative, and I take the power down. I want to do n times b. So I've got that 2 that used to be the exponent, and so I want to multiply that by the 3 that was out front of the x. So 2 times 3 becomes 6. And then I've got the x variable there, and then I have to subtract 1 from the exponent. So really, if I wanted to be clear, I could have said that dy dx equals 3 times 2 times x to the 2 minus 1 power. But again, that all becomes basically 6x to the first power, just 6 times x. Those are really the two that we're going to need. There's plenty of others. Again, you have sines and cosines and weird things like that. But we won't really need them for what we're going to do. Let's say you have a big equation like this, and when you saw that total benefit or total cost line, you might have a couple different x terms in there. You might have an x to the first power, an x to the second power, x to the third power. When we're taking the derivative, we should do one at a time. So there are 3 terms there. There's the 100, there's the 3x squared term, and then there's the 5x term. So let's just break it down and think about each one individually. Well, the 100 is a constant because it's not being multiplied by x, it's not being transformed by x at all. It's just a regular number just by itself, and it's always going to be 100 no matter what value x takes. So the derivative of y with respect to x on that first term just becomes 0 because 100 is a constant. The 3x squared term, we already figured out how to take that derivative. 2 times the 3 times x, and then you subtract 1 from the exponent, so you get 2 times 3x to the first, or 6x. And the 5x, the last term in my y function, is actually 5x to the first power. So when I pull the 1 down to multiply it out front of the 5, it just becomes 5 again. But then it becomes 5 times x to the 0. And if you remember from your math class, anything to the 0th power becomes 1. So again, if I wanted to expand this and show you exactly what's going on, that last 5x term, the derivative would be 1 times 5 times x to the 1 minus 1 power, or 1 times 5 times x to the 0 power, or 1 times 5 times 1, or just 5. So the derivative of y with respect to x, after we've done all of the terms, becomes 0 plus 6x plus 5, or just 6x plus 5. Again, maybe push pause here, go back to your Excel sheet and do it again. Make a column of y, make another column of just x, and again, maybe try doing your x's from 0 to 10. In your y column, enter in that entire formula. Your first cell will be equals 100 plus 3 times probably a2, whatever that cell is, squared plus 5 times a2, whatever your x column is. And then you'll get this graph of y, or you can make a graph of y. So see what that function looks like, and it's going to have some curvy shape to it. And then make another column, a third column, which is your derivative column. And it'll be, equals 6 times your x column plus 5. And if you graph that too, probably don't do it in the same graph because it's probably not going to look very good together. But if you made a separate graph where you had x as your horizontal axis and your dy dx as your vertical axis, you should be able to see some correspondence, some relationship between the slopes of the y picture, the y function, and the slopes of your derivative function. When the y function is increasing, then the derivative function should have a larger positive slope, something like that. If we look back at the demand functions we had before, we had the demand, or the quantity demanded of an item depended on the price and the income and lots of other variables. So if I want to take the derivative of y with respect to x, I see there's this other variable z there. And what do I do with that? Well, you can basically consider anything that's not an x, you can consider that as a constant. So if I want to take the derivative of this y function with respect to x, then I really don't need to worry about that 5z. I can treat it basically the same way I treated the 100. And just say, well, the derivative of y with respect to the x variable is 0 plus 6x plus 0. Because again, the 5z term has no x in it. So if the x changes, the 5z term isn't going to change. So it just becomes, its derivative just becomes 0. If I said, well, what's the derivative of the function y with respect to the variable z? Well, again, the 100 doesn't matter, and now the 3x squared term isn't going to matter because there's no z in that. And that basically becomes 0 too. And you still have your 5z to the first power. The derivative of that becomes just 5. If you did a picture of y equals 5z, you'll see that it's a straight line, this constant slope upwards. The value of the slope is going to be 5. And that's what the derivative told me. Here's an example we can do. Let's say we have this direct demand equation, Q equals 700 minus 100p. We want to know what level of Q, what quantity, could we try to sell to maximize our sales, maximize our total revenue. We might be able to just sort of guess, and again, pick different quantities and see how much revenue comes in and just sort of guess from that way. But why go through all that legwork? Why don't you just solve it, and you'll know exactly the amount of Q in one step. You don't have to do all this guesswork. The first thing we need to do is to swap things around. Our choice variable is Q. We want to pick the quantity to maximize our total revenue. So we have to make sure that Q is a independent variable to pick from. So we got to do this inverse demand function first. Algebraically swap it around. You get P equals 7 minus 0.01 Q. Total revenue is price times quantity. So I've already got an equation for P that I just found. And let's multiply that by Q again. So 7 times Q becomes 7Q. The minus 0.01 Q times Q becomes 0.01 Q squared. So I've got an equation for total revenue. And again, maybe back up and push pause, go to Excel, make an equation, make a graph of what the total revenue line looks like. And it's going to be hill-shaped. And you'll see there's the top of the hill there. And maybe if you want, you can kind of eyeball it somewhat, see if you can figure out where the top of that hill is. If you don't have that, if you don't have something that looks like a hill, it might be that your Q isn't big enough, or maybe your Q is... So if it looks like your total revenue line is continuously upward sloping and you don't see it flattening out, you probably need to pick bigger values of Q. Maybe instead of having your Q's go from 0, 1, 2, 3, maybe have it go 10, 20, 30, or 100, 200, 300, maybe experiment a little bit. The total revenue line should look kind of hill-shaped, so you don't have to play with the scale of your Q values. Well, I want to know, where is the top of the total revenue hill? So I want to know an equation for the total revenue line. I want to know marginal revenue, which again is going to be how is the total revenue changing when I have a change in Q. If I want to get to the top of the hill, then I want the equation for that marginal revenue line to equal 0. I want to be able to pick a Q that will cause marginal revenue to be 0, because that will mean that I've picked a Q that got me to the very top of the total revenue hill. So I had my total revenue equation from before, 7Q minus 0.01 Q squared. So I need to find the derivative of that, and that will give me marginal revenue. So 7Q, the derivative of that term, just becomes 7, because it's 7Q to the first. 1 times 7 times Q to the 0 just becomes 7. That 0.01 Q squared term, the derivative of that, the 2 comes out front and gets multiplied by the 0.01, so I get my negative 0.02 Q to the first, or just 0.02, negative 0.02 Q. To get to the top of the hill, actually, well, the equation of marginal revenue just by itself would be marginal revenue equals 7 minus 0.02 Q. But if I want to get to the top of that total revenue hill, then I can set that equal to 0, because I can say, well, I want marginal revenue to be 0, because I want it to be at the point where the slope of the total revenue line is 0. So I can just say, let me set up this equation, 7 minus 0.02 Q equal to 0. And then I can solve for that. I can say what value of Q is going to make that situation happen. And if you kind of algebraically rearrange things and solve it, you get a Q equal to 350 units. So go back to your total revenue line, first of all. And again, you might have eyeballed a particular amount that you thought was going to be big enough. But you should verify that that quantity of 350 is exactly at the top of the hill. And if you made your table over on the side from which you made the graph, you had these values of Q going down and the values of total revenue going down. Look at you might not have actually typed in 350 exactly. Maybe you went from 200 up to 300, and so there's a gap in between. But if you were to kind of expand it out a little bit and plugged in a value of, well, do this, put in a Q of 349, and then a Q of 350, and then maybe a Q of 350.2 or something like that. You should find that the Q of 350 is exactly the highest amount of total revenue you can possibly get. You can't improve on that. Well, there you go. I already cheated a little bit for you.